Okay, this is Mr. Barron. We're going to be studying kinetics. Primarily, we're going to be studying how to identify whether a reaction is first order, whether it's second order, based on data. This is also going to allow us to study a change in concentration over time. Now we're actually using equations that are provided for us on the equation sheet. These three on the bottom left of your formula sheet are the ones we're going to be using for the rest of this chapter now. And the top one is for first order reactions, and the second one is for second order reactions. So take your paper, chop it into half. On the left side, make that first order reactions. On the right side, please make it second order reactions. Now, for these reactions, we're assuming what's happening is we have some sort of reaction like A plus B producing C for each. So for the equations I'm going to be writing out, we're just going to be studying only one reactant. And for first order reactions, it's the first equation in the kinetics equation section of your equation sheet. So let's go ahead and copy it down. It's the natural log of the concentration of A at time t minus the natural log of the concentration of A at your starting time equal to kT. All right. And it's actually negative kT, so make sure you have that minus right there. And of course, I'm copying it directly from the equation sheet. For second order reactions, it's 1 over the concentration of A at time t minus 1 over the concentration of A at the starting point of your reaction equal to kT. So both of these will be provided for you on the equation sheet for your test, so you don't really need to worry about memorizing them as opposed to what you did for the rate law and the previous equations that we were using in this class. So now what we're going to do is we're going to study specifically how we can rearrange this equation and look at the data being represented over time. So what I'm going to do is I'm going to rearrange this equation such that it is represented as the natural log of A at time t equal to negative kT plus the natural log of A. So what I've written up here is something that we can graph. So this can be represented as y. This can be our slope, negative k, as m. This is x, or time t. The natural log of A is b for our graph. So for a first order reaction, if we have a graph that looks like this, and we have the concentration change A on the left here, and we have time in seconds on the x-axis, over time, reactant A is going to be disappearing. And of course, it'll be producing reactant or product C. What we can do is we can take the natural log of A, and when you take the natural log of an exponential decay, what it does is instead of it being exponential, it makes it linear. Now I know I didn't draw the lines. This top one should be a bit more exponential, have a little bit more of a curve to it. So you know a reaction is first order if when you graph the natural log of the change in concentration for A, that you'll get a linear relationship. That's when you know it's actually going to be first order. It's second order, going to this equation over here, if you have A, and just like first order reaction, you'll see a possibly slight exponential change. You know, it's second order if you graph 1 over the change in concentration of A over time in seconds, and then you'll get a positive linear relationship. Now, by the way, this should look a little bit more like a straight line than I drew it. And this should look a tad more like a curve. It should be a bit more curved than the other one. The linear relationship that you get when you graph 1 over the concentration, you may be like, well, crud, how do I remember this? Darn it. Well, you've got these nifty 2 equations that are provided for you on your equation sheet. Notice this one has natural logs for the first order, and this one has 1 over the concentration change. Here we go. All right, now I'm going to give you an example problem, and I'm actually going to get this example problem from the textbook. And we're going to be using sample exercise 14.7, but I want to walk you through it with words so that you can understand it a bit better. In this question, if you look on page 588 of your textbook, what you're going to see is that it tells you have this decomposition of a certain incesticide of water, and it follows first order kinetics with a rate constant. So when I hear initially in this problem rate constant, I think K. And K is going to be 1.45 years with inverse seconds. And it's going to be at 12 degrees Celsius, but as long as our temperature stays the same, we can assume that K will stay the same. K only changes with temperature. So now what we're going to do is we're going to look at a certain concentration. And the initial concentration, it says, is that we start with a concentration of 5.0 times 10 to the negative 7th grams per centimeters cubed. They tell you it's a first order reaction, and when you hear it's a first order reaction, the first thing you should do is write down this formula, which is the formula we use for the change in concentration at specific times for first order reactions. And this is coming from right here on your formula sheet. The top one's first order, the second one's second order. Okay, now what I'm going to do is I'm going to look for my given information. Well, I know K, so that one is taken care of. I know K. And the question is asking for, what's the concentration after 1 year? So I know another piece of given information is that 1 year passes by. So I know time. And what it's asking for is what's the concentration after 1 year? So at time t, that's what this variable represents. I'm trying to solve for the concentration of A, whatever I started with, after so much time has passed. And that's what the t down here to the bottom right means. Now if I look at this natural log, A at naught. What this means, that's what I started at. Whenever you see this 0 as a subscript, that means you're starting at that particular concentration. So I'm actually going to go ahead and just plug in my numbers here. I know I'm solving for the natural log of A sub t here, minus, and then I know my starting concentration. My starting concentration is right here, natural log of 5.0 times 10 to the negative 7th grams per centimeters cubed is equal to K, negative K, which is 1.45, which is years inverse seconds, times the time, which is 1 year. So my years are going to cancel out, and I'm going to end up with negative 1.45. Now I have to get natural log of A sub t by itself. I still have this natural log that I'm going to have to move to the other side of my equation, but I'm going to write it out first. I want to make sure that I have this clearly written out. So I'm going to add this to both sides and get the natural log of A sub t by itself. So it's going to be negative 1.45 plus the natural log of 5.0 times 10 to the negative 7 grams per centimeters cubed. Okay, what I would do, what I recommend doing, is getting the numerical answer for what I have here on the right. So on my calculator, what I'm going to do is I'm going to take the natural log of 5.0 times 10 to the negative 7, hit enter, and I'm going to add that to negative 1.45. And the answer I get is negative 15.96. And now I have to figure out what A sub t is. Now you'll notice something on your calculator. My natural log button's right here, and right above it is e to the power of x. So natural logs are base e. So if I want to get A by itself, I'm going to have to take e to the power of that natural log and e to the power of negative 15.96. So in my calculator, I'm going to type in second, then I get e to the power of negative 15.96, cap off the parentheses, then I get my answer. And that's the concentration for A, which is 1.17, or I could shorten it up to 1.2 times 10 to the negative 7th grams per centimeters cubed, which is the correct answer. The tricky thing here is that I don't know how many of you are experienced with natural logs or how well you remember them from your math class. If you want to solve for what's inside of a natural log, you take it to the power of e. So this goes away, and you have just a sub t, and you have to take e to the power of negative 15.96. As a brief review, e is 2.718. It's just a long number, just like pi, and it's found in a lot of natural things like shells and, I don't know, interest in your checking or savings account. E is the base of a natural log. So natural log base e is what the natural log is the base of, not 10. E is definitely not 10. You can figure out what e is if you take e to the power of 1, and it ends up being a really long number, 2.71828. It's just like pi, it's a long number. If you guys have any other additional questions about natural logs, please let me know. So now that we've solved this problem, we've seen something that there's two equations here. There's this one, and then there's this one. And as long as you know 3 of the variables, you can solve for the 4th. There's only 4 variables, and there's algebra that we can do to solve for the unknown. Now what we're going to be looking at are half-life equations. The half-life equation is actually on page 591. It's not on your formula sheet, so you just need to know how to use it. And it's that half-life is equal to negative the natural log half over k. So a half-life equation is actually pretty darn useful. By the way, if you take the natural log of half, you actually end up with 0.693. But I'm going to leave it written out like this. If you're graphing a change in concentration, say I have A disappearing again, and I have time on my x-axis, and say it's first order, so got a nice exponential change here. If half-life is when, say you're starting at concentration, and I'm just going to make up imaginary numbers here, it's going to be 100. And once the concentration gets down to 50, whatever that time is, that's going to be your half-life. And then once again it gets down to 25, that's going to be your half-life. And we use the symbol T sub half to represent our half-life. So there are problems in this chapter where you're going to have to solve for half-life. And it works particularly well when you're doing the half-life of a first order reaction. So again, I'm going to put a box around this. This works for first order reactions. Okay? Now I'm going to do an example problem for you that's going to illustrate this concept. An example of a half-life problem, I'm going to use a problem from the end of the chapter that's actually not assigned, but it's very similar to some of the others that are. I'm going to do number 36 on page 620. So on number 36, you're given information about k, given k as a constant, and you find that k is 1.6 times 10 to the negative third inverse years. And this is for an isotope, americium-241, which is used in smoke detectors. And then you have, by contrast, you have another isotope, iodine-125, which is used to test for thyroid functioning. It has a rate constant of radioactive decay that's much different. It's k equals 0.011 in its inverse days. And you have to figure out what the half-life is for each of these. Now, a half-life is a good representation to figure out how much of your sample is still remaining, or how long does it take, I should say, for half of your sample to still be remaining. So this is the americium-241, and I'm going to use the equation that I wrote up above. So the half-life is equal to minus natural log of a half divided by 1.6 times 10 to the negative third inverse years. So I'm going to go ahead and plug that in. So the natural log, 0.5, and get that answer. And then I'm going to divide it by 1.6 times 10 to the negative third, and I hit enter. And then it's a negative answer. I have negative 433. But remember, there's this negative sign on the front, so that makes it positive. So my half-life is 433 years. So for this k, all you had to plug it in is to find how many years have to pass for half of the americium-241 to go away. And this is why we use americium-241, because americium-241 is really convenient. It decays at a rate such that you'll have plenty of americium-241. It'll be a long time before you don't have enough for the smoke detector to actually work. Now we're going to do one last problem. And this last problem is where you have to identify whether something's first order or whether it's second order. Sometimes you'll be given data and you have to identify whether something's first or second order. Say I have a data table and I have time in seconds and I have concentration of my reactant in molarity. And at 0 seconds, 5 seconds, 10, 15, 20, the concentration is dramatically changing. It's decreasing. Start off with 0.100, 0.017, 0.0090, and 0.0062, 0.0047. Right. What you want to do in your table is that if you want to figure out if it's first or whether it's second order, what you're going to do is you're going to have one column where you take the natural log. You're going to plot the natural log of your concentration at each time. So if it's first order, and I plot the natural log of A at each time on this graph here, what I'll see is I'll see a straight line. If it's second order, I want to plot basically the reciprocal of the concentration. So 1 is going to be the natural log of A, which in this case is going to be the natural log of NO2. And then over here, I want to plot 1 over the concentration. And then you have to make a plot. So in my calculator, and it's actually even more convenient to use a program like Microsoft Excel for this. So natural log of 0.1, enter, and I get negative 2.3, natural log, and so forth. And then you move down. You basically get each of these pieces of data. Then you get each of these pieces of data using this as your starting point. Then you're going to want to make 2 graphs. And if you see a graph where you have the natural log of your initial concentration, which is going to be nitrogen dioxide in this pond, if you see it go in a straight line like that, you know it's first order. And don't forget your x-axis this time. If you have a straight line going up, you know it's second order. Of course, you're plotting 1 over the concentration of A in times on your x-axis. If you guys have any other additional questions, please see me. I'm available for tutoring Monday after school prior to class on Tuesday. Thank you.